Good afternoon. I'm very happy to see you here for the Rosseland Lecture of 2015. And I'm especially happy to see so many distinguished and eminent guests. Amongst them, the Danish ambassador, Torben Brylle. And we're all here to see Anja Andersen give a talk about dust, making, baking, and breaking dust in the interstellar medium. Now, Anja has stuck with this subject for quite a while, of dust, or støv, or dam, or whatever you want to call it. And in fact, she did her PhD on the subject, looking at meteorites, at asymptotic branch stars, and at Supernovae, with Uffe Grø-Jørgensen in Copenhagen, which she finished in 1999. Thereafter, she went to Sweden, to Uppsala, and Bengt Gustafsson, and stayed there doing a postdoc for 2.5 years, returning after that to Copenhagen and Nordita for another 2.5 years before she settled down in a place called Dark, and she's been there ever since, i.e. 2005, and we're all very happy to see you give the lecture today. Welcome.
Thank you. So thank you, Viggo. And I hope that in Denmark, people often get disappointed when they see me because they expect the other Anja Andersen. And normally I don't have that problem when I go abroad, but I guess in Norway I might have that problem. So I hope I'm not disappointing any of you for not being the right Anja Andersen. So I'm the dusty one, not the one with the handball. I'm a bit older, so I was there first. It's not my problem that she has the same name. I can reveal that both Anja and Andersen is a very common name, so there's like 55 of us at around the same age in Denmark. So I work on dust, and I'm at the Niels Bohr Institute, where we are not that many women, and I hear lots of jokes about the women being stuck with the dust and let the women take care of the dust. And I must say that when I was a student, if anyone had ever predicted me or told me the fortune saying you're going to be an international expert in dust grains, I would think, God, that sounds really boring. Maybe I should change career. So I hope I can manage to convince you that dust is actually really, really interesting. And the most interesting about it is that even though when you clean at home, all the dust comes in and you don't know where it comes from and you can't get rid of it, but in the universe, it's actually quite a mystery where the dust comes from, because it's very hard to form dust, and still we see dust in huge amounts in the different galaxies, and dust is important, but we just don't know what the origin of it is. So that's what I've been working on ever since. Been working on it for 20 years. I hope to solve it, and the good thing about it is I've been thinking I've solved it like every second year. I thought I was on to the track, and then it turned out not to be it, and I'm going to end, my last slide is going to be my current best theory that I'm going to give to you. And as we are running out of objects, then if this one doesn't work, then we are really lost, because then we don't have anything to offer. So I'm going to take you through the different assumptions we had and why they turned out to be wrong, and why we are still left with this mystery. So what you see here is interstellar dust clouds from our Milky Way called the Eagle Nebula. And it is such that interstellar matter actually really matters, because even though there's not that much dust in the galaxy, then if we had no dust clouds in the Milky Way, then the Milky Way would actually be 1 billion times brighter. So even though astronomers often hate dust because it's in the way, then there wouldn't be much astronomy without dust, because then the Milky Way would just be lighting up the whole night sky and we wouldn't be able to see much. So the reason that dust is important is that it actually determines how most of the stars in the Milky Way end their lives. That's what we call cool red giants. They have to lose a lot of mass, and this mass loss is dust-driven. It's important for star formation. We cannot explain how stars like the sun are formed without having dust. It's essential for planet formation, and it's crucial for forming molecules. So the reason that we have amino acids and alcohol and sugar in the interstellar clouds is because they form on surfaces of dust. And then, of course, it's very, very irritating for observers. So the reason that I'm part of the Dark Cosmology Center is actually because they want to see to the end of the universe and determine what it's all about. And they want to not be bothered by the dust. So they want to be able to come to me and say, get rid of the dust for us, please, so that we know what we're looking at. So the reason that, so just to give you some basic facts, because it might not be clear, you might have different images. When I talk about dust, you might be thinking about the sort of the big things that you find underneath your bed. But actually, I know none of you are smokers, but maybe you once knew a smoker, and you have seen the little sort of smoke particles that you can see in cigarette smoke or in the projector light or coming in when the sun shines through your window on a sunny day. So it's like little smoke particles. When I say dust, I think of little smoke particles. And it's such that 1/5 of the Milky Way, which consists of stars and planets and other what we call baryonic matter, so that's everything which is not dark matter. So 1/5 of that is present in the contents of gas and dust. And of this 1/5, it's only 1% which is actually dust grains. So actually the Milky Way is not very dusty. To some extent it is the dream of every housefrau. It's quite clean. But that 1% actually blocks out so much light that the Milky Way would be a billion times brighter if it wasn't there. These smoke particles probably consist of carbon, oxygen, silicon, magnesium, aluminum, and iron. And if any of you are sort of an amateur geologist, then what you can think about is soot from your barbecue grill or sand from the beach. That's basically the two different types of dust that we have in the universe, so soot and sand. So the reason that dust is actually important is that if you look at what astronomers and physicists call the electromagnetic spectrum, from all the different wavelengths, it's such that astronomy is a very inclusive science. We love all wavelengths, not just optical light. We like X-rays, we like microwaves, we like radio waves, and we call everything light. So if you look at what you can observe at the different wavelengths, then it's such that apart from the CMB, which lots of people here in Oslo works on, which sort of supersedes it all and has the highest signal, then optical light, which is the green one, and infrared light, which is from the dust, is sort of the two most prominent features of what you can observe in the universe. So it looks like this. So you have optical light, which is direct starlight, so to speak, and then you have the cosmic dust shining up in the infrared, where you should imagine these smoke particles. So the stars actually shine on the smoke particles and heat them up, and then you see the heat glow from the dust particles. So that means when we observe distant galaxies, then half of the information that we can hope to get from these galaxies by observations is hidden in the infrared area, it's hidden in the dust. So this is the starlight directly. This is the sort of secondary information we can hope to extract to understand galaxies better if we understand what dust grains are actually sort of reflecting the stellar light, if we understand what we are looking at. So that's actually why dust is awesome. So just to show you some recent observations. So this is a part of the Milky Way observed by a satellite called Planck, which should be very well known to some of the people in the audience. And this is the resolution of the Planck when you go into details. The infrared satellite Herschel, this is the resolution that we get when the Herschel satellite, which can observe in the infrared, look at the same area. So actually a lot of the knowledge that we have now about dust in the Milky Way is due to this satellite, the Herschel satellite, which is quite unique and has given us a lot of new insight to what the dusty areas are, and made it possible for us to understand star formation better and planet formation and also the origin of dust. So the questions that I've been wanting to answer and still are working to answer, and which you need to answer in order to interpret the signal from the dust is, so what elements are present in the dust? What is the mineralogy? So what is the crystal structure? Is it soot, or is it sand, or is it diamond, or is it graphite? What are we actually looking at? What is the morphology, meaning what shape does it have? Are they round? Are they elongated? Are they squared? Are they potato-shaped? Because which form they have will actually influence a lot how they reflect the light. So that will have a huge influence on the light that we observe. And then size does matter. Small grains actually scatter light quite different from large grains, so it's actually important to know their sizes. The big question is, where is the dust formed? Because in order to form dust, you actually need two things to be in place. Because you need your atoms to be close enough that you can actually get them to form a crystal structure, and you need the temperature to be low enough so your dust doesn't melt. And the problem is when you look out into the universe, then where you have high concentrations of materials are in stars, and stars are typically hot. So the combination of having low temperature and high density is not very common. So either you have low density, but then you also have you have so low density that temperature doesn't matter, or if you have high enough density, then your temperature is typically too high. So the trick is to find the places which is sort of the sweet spot where you can have high enough density and low enough temperature. And then when the dust is formed, then we also have to worry about the lifetime of dust grains, because the universe is actually not a very friendly place, neither for humans nor dust grains. It's actually quite easy to destroy dust grains by ultraviolet photons, so they don't live forever between the stars. Eventually they get spotted away and they evaporate if they get too hot. So one of the clues that we have about what type of dust to look for is actually when we look at the gas in the interstellar clouds, then we can sort of see, we can compare the amount of the different materials that we would expect to be there, and then the amount that we actually see there. So the amount that we expect to be there is that we look at what is present in the sun, and then we think the sun is probably a good proxy for the distribution of elements in the universe. And then we look at that proxy and we say, okay, we find a little less carbon in the interstellar clouds than we expect compared to the sun. We find about the same amount of nitrogen as we expect. We find a bit less oxygen. We find a lot less magnesium and a lot less silicon. So based on this, we actually talk about depletion factors. We talk about missing elements. So you can say this is an indirect idea of what the dust is built from, because we say, okay, we're missing some silicon, some magnesium, a little bit of oxygen and a bit of carbon, so that's probably our building blocks. As we have a lot more carbon and oxygen in the universe, the fact that we're just missing a little bit doesn't tell you how much is there, because when you have a lot more, then even if you're missing a little, you can have a lot of dust grains built up of carbon and oxygen. Because these two elements are more abundant, and this is what is shown here. This is sort of the depletion factor. So you have a lot more carbon, a lot more oxygen, and while almost all the magnesium and silicon is tied up in dust. And the same goes for iron and nickel and zinc. Most of that is tied up in dust grains. So you can say we see the dust grains, and then we infer what they're made of out of missing elements in the gas. We think that everything missing in the gas phase must be in the solid phase, and that's what we think the dust is made of. But of course it's not a direct fingerprint, right? It's like looking at footprints from a dinosaur and then try to infer how many heads the dinosaur would actually have when it walked around. So just to give you a really quick astronomy 101 thing, then all the elements, so you have interstellar clouds from which you form stars, and then you basically have two tracks. You have low mass stars and you have high mass stars. And low mass stars, which are stars like the sun, they live for a long time, and they mainly produce carbon, oxygen, and nitrogen, and what we call slow neutron capture, and they live for about 10 billion years. So this is sort of a slow cycle where materials are caught in the star makes some elements, and then eventually it returns it to the interstellar medium on a relatively slow cycle. Then you have the high mass stars, which is a much faster cycle, because the larger a star is, the shorter time it lives. And the high mass stars, they live for a very short time, and somehow they're very generous because they produce basically most of the elements. They produce iron and uranium and gold and all the other interesting elements. So they live short, and they produce a lot of elements and return them to the interstellar medium on a relatively fast time scale. So all stars basically are divided into these low mass stars, which live long and have a slow cycle, and high mass stars, which there are fewer of, but they live shorter time and they have a shorter life cycle. Then, of course, the question is, okay, so we know we have a good idea, we think, about where the elements are formed. We have a good idea of which elements are missing, but do we actually have any direct clues of what kind of minerals we're looking at? What is the type of dust grains that we can find in space? And we actually do have some clues, because in 1987 it was found that a little bit of the dust that you can find in the most primitive meteorites are actually original stardust, which has survived the formation of the solar system, which you can extract out of the meteorites, and then you can measure them directly. So that actually gives us an idea what types of dust do we expect to find. And also, what do they look like? Which shape do they have? So we get some indication from this. And big was the surprise back in 1987 when it turns out that most of the dust you find in meteorites are actually diamonds. And the second most abundant is silicon carbide. That's what you find on sandpaper when you do housework. Then there's graphite and aluminum oxide, also called sapphire. And then you start thinking, okay, so stars actually sprinkle diamonds and sapphire. That does sound like every woman's dream. And then you start wondering, does that mean that stars actually do all these very hard phases? Or do we see a selection effect here? Because we are finding some dust grains that survive the formation of the solar system, were incorporated into meteorites, and not the least, the way we get them out of the meteorites is actually that we take a piece of meteorite and then we boil it in acid for months until we have just pebbles left, and then we sort out the dust. So maybe stars don't only make these refractory phases, maybe that we also see a selection effect on what we are picking out in the laboratory. So now we're actually trying to be a lot more gentle, which is a bit slower, but that's the good thing about PhD students, right? They have lots of time. You can get them to pick out little dust grains and see, do we only have diamonds and sapphire, or do we also have more fragile dust types present in the meteorites? So you can say, okay, how can she know? How can I know that these dust grains are actually direct stellar specimens and haven't been altered during the solar system formation? So the reason that we think that these are actually dust grains that have survived the formation of the solar system is then when we look at what is called the isotopic ratio, so we look at the elements that these dust grains are formed at and the relative abundance of different elements, then if it was formed in the solar system nebulas as part of the solar system, we would expect them to lie either here in the middle of the graph or around this red line on the graph. And where our measurements are actually lying is we see that it's peaking away from here, and we actually see that there is a huge spread around the solar system. And when we then look at observation from stars, we can actually see that certain types of stars produces these abundances very readily. So we think, okay, that's awesome. We have a direct indication. We have some stardust in meteorites. We have some stars that have the right isotopic elements that looks like a clue that we can actually combine. So we do believe that these grains are actually real stardust. It's real stellar specimens. So what we have from pre-solar grains is that we are quite sure that we have dust which originate from stars. What we're not sure about is whether we have an objective sample or we have a biased sample, because maybe we only see the most refractive dust grains because they're best at surviving. So it might not be that all dust we see between the stars in the interstellar medium is these types of dust, because maybe we see what is better at surviving instead of seeing sort of the normal species. But if we just look at what we have from the meteorites, then the conclusion would be that most of the dust is formed in stars like the sun. So the sun in 5 billion years, when it runs out of hydrogen in the center, then the sun is going to expand out to the orbit of Mars. And when it does that, then the outer envelope of the sun is going to be so cold that the atoms are going to combine into molecules. The molecules are going to combine into dust grains. So we'll actually have dust grains forming in the end life phases of stars like the sun. And then this dust will be blown away as the sun turns into what we call a planetary nebula. So based on the meteorites, we can conclude 90% of the material we find in the meteorites come from these types of stars. 10% comes from the high mass stars, the ones that explode as supernovae. And then we have some rare things that come from other types of stars. And then that should be pretty clear. Then most of the dust must form in solar type stars. So that's actually how my career started out. I was absolutely certain. All I had to prove is how these stars, they formed the dust. And once I've done that, the nail was in the coffin. We knew where all the dust came from. A little bit of contribution from Supernovae, but who cares, right? They might make all the elements, but these stars made all the dust. And that seemed fair enough to me. You know, some guys get to make all the elements and the other ones get to do the dust. So just to give you a short overview, so what we have is, from the pre-solar grains, we have an idea of the grain type, the grain size, and the shapes, the morphology. From looking at what we call standard abundance distribution, so which elements we have in the interstellar medium, then we sort of get an idea of what different elements we have to build up the dust grains from. We have from stellar evolution an idea which stars actually produce the different elements. And then from what we call depletion patterns, so what elements are missing in the interstellar medium, we have a pretty good idea of what is locked up in the solid phase. So supernovae, we actually, for a long time, we were very certain that they were not very important. And one reason was that we didn't find them in meteorites, but another reason was that the most studied supernovae, which exploded in 1987A, when we looked at how the spectrum of that supernovae, how much of the light were missing because it was absorbed by dust, it was just a very, very tiny fraction. So actually it turned out that there was just a tiny fraction of dust in this type of supernova, and that fitted very well with our image from the meteorites, so everything seemed to point in the same direction. Supernovae don't produce much dust, but AGB stars seem very efficient. So my career turned into doing theoretical numerical modeling of how these AGB stars could form the dust. So this is sort of a sketch of the models that I did. So you have the core of the star here, and then you have the outer envelope where you have what is called convection, meaning that you have material moving from the inside of the star to the outer surface. So you have elements moved up from the interior of the star to the surface of the star, where it can then form different molecules. And then your molecules can later go in and form dust grains. And which molecules you form actually depends on a very nice little detail about chemistry, because if you look at the binding energy of the most simple molecules, then it is such that carbon monoxide is actually the tightest bound molecule. And that means that if you have carbon and oxygen, they will readily go together, and once they go together, they don't want to part. They're going to stick there as a carbon monoxide molecule. And for these stars, that actually means that depending on whether you drag up carbon from the interior of the star or you don't drag up carbon, then whether you have sort of a surplus of carbon, then you will form some molecules and you will form sort of soot. You will form carbon-based dust grains. While if you don't drag up enough carbon, then you will have a surplus of oxygen, and then you will form oxygen-rich molecules. And then the chemistry gets a little harder, because the most likely molecule you can form with oxygen is water, but it's too hot for water. So you therefore will form all kind of weird molecules, and eventually we assume that you will form some sort of sand or silicate, as we call it. So some sort of sand material. And I don't know if you've ever been bored at a beach, but if not, then try, because it's quite exciting. Look at sand on the beach. It's really incredible, right? You can have sand grains which are completely transparent, like glass, and then you can have some which are red, and you can have some which are completely black, and they're all silicates, and the only difference to the different colors depends on what elements are part of them. So most of it is silicon and oxygen, but if it contains a little bit of iron, it's going to look more black. If it contains a little bit of magnesium and aluminum, it's going to look more red. And if it only is silicon and oxygen, it's going to be transparent. So next time you go to the beach, just remember, sand is not just sand. Sand is many different materials. Silicates is a whole zoo of different materials, and quite fascinating. And as it looks different, that means that it reflects lights differently, and it lets lights go through it in different ways. So that's important for astronomers to know, how do these dust grains actually interact with the light. So the way that we understand the AGB stars is that once you form these dust grains, then what we think is happening is that you have a dust grains, then you have the photons, which is the light that you form within the star, which actually gets absorbed by the dust grain. And then the dust grain emits or scatters the photon, which actually gives the dust grain a push. That push means that it bumps into one of the molecules, and that molecule is then going to bump into another molecule, so you actually get sort of a push on the dust grains, and the dust grains is going to bump into the gas, which is going to drag the gas along. And we think that's a very nice explanation for how you form what we call planetary nebula, and a way to understand why all these so-called low-mass stars can end up as white dwarfs, which have a relatively low mass compared to the original mass of the star. So the star needs to shed off a lot of mass, and we think that's due to dust-driven mass loss. So we're quite content. We think, okay, this works. We can form the dust in these stars. So we actually have 3 different kinds of these type of stars, depending on whether they drag up most carbon or they don't. So the idea is that most of your material is going to be locked up in carbon and oxygen, in carbon monoxide, and then you'll either have a surplus of carbon, or you will have a surplus of oxygen, or you will have sort of the in-between, where everything is locked up, and then you don't really form much dust. So you have these 3 different types. So this is going to form one type of dust, this is going to form another type of dust, and this is not going to form any dust, and that should be it, and that was the theory, and we were very happy. And then, of course, you have to deal with observers, right? And observers, they have a telescope, they go out and observe, and you want them to observe something that proves your theory, then you are happy. Unfortunately, observers haven't understood that's their main purpose in life. They go out and observe things, and it doesn't always prove our theories. Because what they actually saw when they started doing detailed observations of these stars is that we might have 3 different types of stars, but you can't really tell in the way that they shed off the mass, because they have similar wind velocities, they have similar mass loss rates. They are actually equally good at sending off the material. And that's actually quite strange and hard to explain when you do the theory, because if you have a star that forms soot, right? So imagine you have a star and it forms soot which is completely black, then it's actually very easy to understand how the dust is going to be driven away and how the star is going to lose the mass, because you have completely black dust. If you form sand, then you're going to be in a little bit of trouble, because if you form sort of the iron-rich sand, which is black, then everything is fine. It works just like soot. You can explain everything. But if you look at sand at the beach, only a little bit of it is black. So we were thinking about how do these stars, why do they actually produce equal mass loss when they form different type of dust? The fact that they look so similar should maybe indicate it was the same type of dust, what is actually going on. So I went back to the laboratory to try to understand more about silicates, to find out what is the difference. So these are laboratory measurements where I have measured different types of silicates. So imagine me in the laboratory just putting in sand of different colors into a spectrograph, and then see how it actually absorbs and scatters light. So this is what you see here. How do different types of silicates absorb different types of light? This is where these B stars, the cold red giants, send out most of their light. So this is sort of the important wavelength range. The black one is how the carbon works. And then you can see the green one, that's pure iron. And then we have 3 different kind of sand, and what we can see here, or silicate, is that if you have iron-poor silicates, they actually don't absorb the light very much. They will not be very good at being moved away from the star or actually pull the gas away from the star. So that must mean that the silicates that we form should be somehow iron-rich. Then we thought, okay, there's one problem with our model, because we made what we thought was a reasonable assumption. So we wanted to prove it's reasonable, and you do that by assuming something else and show that you get the same result. So what we assumed was that the dust and the gas would probably have the same temperature in these outer envelopes of the star, because the dust and the gas were bumping into each other. So it seemed reasonable to assume they had the same temperature. So we tried to do a more sophisticated model where we calculated the dust separately from the gas and assumed they had different temperatures. And we should never have done that, because then nothing worked ever again. So this is a bit of a busy plot. But the thing to take away from this plot is what we showed was that around the stars which make silicates, it was just not possible to form the iron-rich silicate, because iron is so good at absorbing stellar light, and iron is such a good conductor, so that your dust grain would get so warm so fast that it would melt. So every time you formed the little iron-rich grains, it would actually evaporate right away. So what we showed is you had to be quite far away from the star to be able to form the iron-rich dust grains. But if you were quite a bit away from the star, then this would not explain how these stars actually lost mass. So we were in great trouble actually understanding how these stars could actually send out. So we had sort of 2 problems. One, how do these stars get rid of their mass? And the other problem is, where are the silicates then formed if they don't form in these oxygen-rich stars? So Susanne Höfner from Uppsala University came up with a sort of a neat idea, where she said, okay, it's not a problem. If you assume that the dust grains are very, very large, then you can actually have them scatter the light off in such a way it's going to work without the iron. And that works actually, so now our numerical models work. So the thing I don't like about it is that we have similar types of stars with different chemistry, and they need very different types of dust grains to work. And I like having one explanation. So at the same time that we were struggling with this, having problem actually explaining how the AGB stars could produce dust at all, then another set of observations came in, and that was that the cosmologists, they got really good telescopes, so they had like the Hubble Space Telescope, and they started being able to see galaxies at a very large distance, so at a very long, very early in the universe. So that they could see great distances, and what they found is, so the story that we had, let me start somewhere else. So the story that we had for sort of the dust formation in the universe was, so you have Big Bang. Big Bang makes hydrogen and helium. Hydrogen and helium are a bit boring. Out of that you can make stars. then you could make two types of stars, the high mass stars that enter supernova and the low mass stars. The low mass stars, they live a very long time, and they are in this theory, we had the ones that make dust. And that actually means that it will be several billion years before these stars die and start forming the dust. So you actually had a very nice early universe which was very dust-free, because it would actually take a while until you had the elements, and then you could start forming the dust, and everything was nice. And then again came the observers, and they got really good telescopes, and they looked at very distant galaxies and said, that might be very well, Anja, that you think that the early galaxies are dust-free, but that's not what we see. We see very dusty galaxies in the very early universe. And then it starts being a little complicated, because how could you actually explain if it's AGB stars that live for a long time that produces the dust, then how could you get the dust in so early in the history of the universe? So another thing that the observers have been telling us is that there seems to be a combination between the metallicity, so how many elements you have of the different types, and the dust actually indicating that once you have elements like iron and silicon and oxygen, they are all going to be locked up in dust. So the amount of elements you have and the amount of dust you have, they go hand in hand. So imagine you have a bunch of Lego bricks, and then you want to build houses out of Lego bricks. So once you have a big bunch of Lego bricks, they're immediately going to turn into houses built by kids and be sort of solid structures. And if you get more Lego bricks, you just get more houses out of it. You don't have sort of free-floating Lego bricks. So once you have metals, you form dust. And you do that at all times. So this is what we call redshift. So this is actually time looking back into the early universe. And what you see is the metal to dust ratio seems to be constant. So it seems that the universe has been perfectly good at forming dust all the time, and very early on. And one interesting thing about this is that you can wonder, how early could you make an Earth-like planet, right? So in the first scenario that I sketched for you, where it takes a few billion years before you have the right stars, and then they have to make dust, and they're not very efficient, then you would actually end up with a hypothesis saying, okay, the solar system formed 4.5 billion years ago, and the universe is 13.7 billion years old. So that means it probably took 8 billion years before you have enough elements to form the first Earth-like planet. So the reason that we haven't heard from any aliens were very easy to explain, because the reason we haven't heard from them was that we were the first generation of aliens in the universe, because we just couldn't have been there at an earlier time, because it just took time to get everything in place. We needed the elements, then we needed dust, then we need to form the planets, and then we were here. What we see now is actually that's a completely wrong idea. You could probably form Earth-like planets very, very early on, like 1 or 2 billion years after Big Bang, which gives you the big open question: if that's true, then why haven't we heard from all these aliens if they have had all these years to actually be ahead of us? So that's just to put it sort of a bit in a perspective. So if you look at back in time, and you look at, okay, once the universe got cold enough that you could start forming the first stars, at what time did you form the first stars, and what we know about how long stars form, then these galaxies, which were observed to be very dusty, they are here at this time in the universe. So this is a timeline. So this is like Big Bang over here. This is the most distant galaxies, and this is today. And what we saw was that the smallest star, which could have lived short enough to end its life, was about 3 solar masses. So all these stars, which we thought were the ones responsible for the dust, they weren't even there where they could start forming dust at this early time in the universe. So another way of showing the same thing is if you, again, look at a certain redshift range, so a certain time period in the very early universe, and then the required dust yield that you need to explain the observations. So imagine we see this little infrared peak, and we want to explain how much dust do you need to explain that peak. And then, of course, when you look at that observation, you have to assume something about the dust. So there's this assumption going in of what type of dust is it that reflects the light. And that assumption can be good or bad, right? So what you see here, the light blue and the dark blue points, they actually correlate. And that's just to show that depending on what you assume, you can get your values either here or there, depending on whether you think the dust is very good at reflecting the light or not so good at reflecting light. And down here in the light brown, that's actually where you need all the data points to be in order for these solar-type stars to be able to explain the dust in the universe. So it seemed very clear. They observe one galaxy and you go, but that's a weird one, right? That's a weird one, you found a weird one, who cares? But eventually they come up with more and more galaxies, and it might sound funny that we could get away with saying it was a weird one, but you have to remember when astronomers have telescopes, right? Then when we look out in the universe, then the larger the distances, the more likely we are to see something which is very bright. And the less likely we are to see something which is necessarily normal, like the Milky Way. So we might actually have a very biased picture of the early universe, because we're going to be able to see like New York and Rome and London, and then we're going to conclude that everybody lives in very big cities, even though most people actually live in very tiny cities that don't send out much light. So it's a bit like sitting in an airplane, flying over Earth, and then you would naturally conclude that not very many people lived in Africa, and the few people who lived in Africa probably lived around Cairo or down in South Africa, because most of it is pretty dark compared to when you fly over the US. So you might actually get a biased picture. But then last month in Nature came this really annoying galaxy. And it's only one galaxy, so I'm still safe, but it's really, really an annoying observation. Even done by one of my colleagues, it's really annoying. So what we see here is actually a normal galaxy. This is a galaxy like the Milky Way, present in the universe less than 1 billion years, so 700 million years after Big Bang. And the reason that we could see this galaxy was actually that it was extremely fortunate. So imagine you have the galaxy here, then you have a group of galaxies, what we call a cluster of galaxies here, and we're sitting here with our telescope. So what we actually saw was that the light from this galaxy was spent around the cluster of galaxies in what we call a gravitational lens, which actually means that the light was magnified 9 times. So this galaxy looks 9 times brighter than it normally would at the distance that we are from it, just because we were damn lucky that nature sort of gave us a natural magnification of this galaxy, which made it possible for us to observe a completely normal Milky Way galaxy which hasn't done anything exciting except for the fact that it actually contains as much dust as we find in the Milky Way, indicating that less than 1 billion years after the Big Bang, you can have a galaxy as dusty as the Milky Way. So, as I know there's some astrophysicists, I'm sure you're thinking the same as I do, is, all these cosmologists, right, who claim that these galaxies are so far away, they use what we call photometric dropout, and who knows if that's actually correct. But unfortunately, this is what we call a spectroscopic redshift. So it's probably okay. It probably is actually present very early on, 700 million years after the Big Bang. So there might be other problems with that observation, but this is not a problem that we can blame on them. So we are now left in the situation where, you have 400 to 500 million years possibly after Big Bang to form dust. So you need a very fast route of dust formation in order to explain that. And the universe has been at least as dusty as it is now, possibly even dustier earlier on. And then you think, okay, so you have 2 types of stars. You had the high mass stars that exploded as supernova. You had the low mass stars, which were like the sun. We have to rule out the low mass stars. They don't live long enough. They don't get to the phase where they can start forming dust. And the more we look at them, they might look dusty, but they're actually not very good places for forming dust, and they don't form very much dust, it seems. So we went back looking at the supernovae, thinking, okay, the supernova we ruled out because we had this one observation of 1987A, and we had the pre-solar grains from meteorites, which indicated they were not important, but maybe we need to take a second look at them and see if they are important. Because when you do models of supernovae, so you imagine you have this big star, and then eventually it collapses in a supernova explosion where it explodes. And it produces almost all the different elements that you have in the periodic table in different ratios. So you actually have a very nice place that right when it explodes, it's a very hot gas. It's not good for dust formation. But then you have this very hot gas that expands, which contains all the right Lego bricks, all the right elements that you need. So that means as the gas expands, it will cool down. So there is actually a time in the history of this supernova remnant where it's very good for dust formation. It's just a very short time. But you have about 20 years where you have sort of a sweet spot where the density of the gas is high enough and the temperature has dropped low enough that you can form dust, but only for a short while, because then the gas gets so thin that eventually you stop being able to form dust. But you have sort of a little window there. And when we do theoretical modeling, and that's the sort of the bless of theoretical modeling, then we can form lots of dust, because how much dust we can form just depends on our assumptions. So if we assume we have lots of elements, we have the right temperature and the right densities, we can form solar masses of dust, no problem. It's so easy. So theory has been predicting for years that supernovae are really, beautiful places of forming dust. The only thing that we couldn't quite determine is that what happens when you have a supernova exploding. So you have this gas moving out, then eventually it will hit what we call the interstellar medium, so the dust and gas clouds that you have in the galaxies between the stars. So when you have an expanding gas that hits some cold gas, which is lying still, then what happens is that the gas hits, and then it actually gets rebounds back, so you actually get what we call a reverse shock, a shock that goes back in. And if there's one thing the dust grains don't like, so it's a bit like, imagine, so you have a lot of snow, right? And then you have this plow of snow. Just keep pushing up snow, and eventually it's pushed up so much snow that the snow falls back on the guy, trying to move the snow, and then suddenly you have no guy anymore. So a bit like that you get this shock front, and then it moves back, and then actually a shock is not very nice for a dust grain. It tends to heat up things and destroy dust grains. So the models had the problem that we can form lots of dust, no problem at all, but how much of the dust that actually survives and gets into the interstellar medium, we cannot decide, because it depends on what number we put into our models of how effective the reverse shock is. So if we say, well, this reverse shock is not important at all, well, it comes back, and who cares, because it's just like a tsunami, and the dust grains are just like a boat in the sea, it's just going to ride on the top of the shock front, and it's not going to touch the dust grains. Then we can get 100% efficiency, and then we have no problem. Supernova can do all the dust. But if we assume that the shock coming back is actually quite destructive, then we have a problem, because then we find out that supernovae don't really produce any dust. So as we could not decide in the theoretical model department, then we did need to turn to the observers and say, will you please go observe some supernovae, because we need an answer here. Are they good at producing dust, or are they not good at producing dust? And the problem with supernovae is that there's not that many of them. So they're not that easy to observe, just because the number is very low. But nevertheless, we had Loretta Dunn out in 2003, and she observed this supernova remnant called Cas A, and her conclusion was there's lots of dust in Cas A. There's like 2 to 3 solar masses of dust. And then Krause came half a year later, and he actually looked at the same data, and he said, no, I don't believe you. You're completely wrong, because this supernova remnant is lying in what we call the plane of the Milky Way. So that means when we look at it from Earth, then we look through a lot of gas and dust in the Milky Way. So he was claiming, you actually don't, the dust you see, you cannot tell whether it's in the supernova remnant or whether it's on the way to the supernova remnant in your sight line. So you're just assembling all the dust that you see in your sight line, and you're attributing to the supernova, and supernova are actually not very efficient at all. And they still have a heated debate about that, so it's still a bit unclear whether there's no dust or lots of dust in Cas A. Then people observed some other supernovae, and depending on who observed it, so Sugarman, he said this supernova had 0.02 solar masses of dust, and then Mikkel came and observed the same supernova and said he couldn't see it. So the observers couldn't really give us any indication either, because they interpret their data in a different way, even when they looked at the same supernova remnants. So we were a bit like, okay, can supernova do the job or not? And that was a big mystery, until the Herschel satellite came and took a second look at 1987A. So remember, I showed you early on a picture of 1987A. It seemed like it didn't produce much dust. We thought it was a bit boring, so we had not looked at it. But anyway, some astronomers were a bit more visionary, and they actually asked for observing time to look at this supernova remnant, and some other observers were actually visionary enough that they gave them the time, even though we all knew that there was no dust to be found. So they looked at at 1987A with the Herschel satellite for a short period, and it looks like this. So this is the supernova remnant that Herschel observed. And what they found was actually that in here, in the magnified, they found actually a lot of dust. So actually 0.4 to 0.7 solar masses. So that means, imagine, basically the whole mass of the sun as a big dust pile, and that's actually lots and lots of dust. So we were many, myself included, when that paper came out. I spent a whole week trying to prove that they were wrong, and as I couldn't, I became a believer, thinking maybe this observation is actually correct, even though it doesn't make any sense. Other people disbelieved them so strongly that they actually went out and got time on the ALMA telescope to see if they could actually confirm that the dust was actually coming from the interior of the supernova and not the sideline or not the molecular cloud around. And they actually showed that yes, there is dust, and ALMA confirmed this. So it seems that 1987A is so far our only one data point that supernovae seem to be able to produce huge amount of coal dust. But 1987A is also a very young supernova. So we haven't yet seen what happens when the supernova expands out to what we call the interstellar medium. So we don't know when the reverse shock sets in, whether, yes, it has proven what the theory already told us, you can form a lot of dust, but it actually hasn't proven whether this dust is going to survive and actually end up in the galaxy from which the supernova is part eventually. So we don't know whether it will actually die once it gets out here. So the verdict is somehow still out. So dust from supernovae, we have large amount of dust. We think that the low mass stars, they can't make the dust in the early universe, and if they can't make it in the early universe, there's no reason to believe that they're responsible for what we see in the Milky Way. Theoretical models predict that supernovae are very good at it. The observational evidence is sort of rare and a bit unclear. So while I'm waiting for some more observers to go out and observe some more supernovae, I have cast my love on a new type of object, which is basically the last man standing, so to speak, of where you could imagine that you could form dust if it turns out a supernova are not going to be efficient. And this is actually in what we call high mass stars. So this is a star before it explodes as a supernova. So there was another infrared telescope called Spitzer, which was flown by the Americans before the Europeans flew Herschel. And Spitzer actually discovered 156 high-mass stars with dusty shells around it, which nobody had expected. And we can't explain what elements it could be, we can't explain what dust types it could be, but the fact that they all seem to have little dust puffs around them, and there's 156 of them that we didn't expect to be there, indicates that this must be something that happens quite frequently, right? Because else we are just at the very rare time in the Milky Way when they're all going to have dust puffs. So that's actually what I'm working on at the moment, trying to find out. So can maybe the supernova stars produce most of the dust before they go supernovae? And that's at that time it's a lot more gentle wind that sends it out into the interstellar medium. So if that dust just can be gently sent into the interstellar medium, maybe that can sort of add up what the supernovae, what comes after the supernova cannot explain. The big question here is, of course, what happens when this star explodes as a supernova? If this dust has not run away far enough, it has to be way out here when this star explodes as a supernova if it's going to have any chance of surviving. So I've showed you sort of 20 years of research where we've gone from thinking we knew exactly where all the dust were formed to now ending at a place where we think we have basically no clue. But what we do have a clue about is that the universe is a lot more dusty than we thought. That early type galaxies are, from my perspective, a lot more interesting than I ever thought they would be, because they actually contain a lot of dust. It means that you could form stars like the sun very early on in the history of the universe. You could form planets around these stars very early on. So planet formation is probably going to have been more efficient at all times in the universe than we expected before. So I would say, even though somehow the conclusion is we still don't know where the dust came from, the hunt for the dust was still quite interesting, because it's given us so many other interesting little side insights to how the universe is functioning, and raised new exciting questions. So with that, I would open the floor for questions, and thank you. So Viggo is going to be the chair that's going to direct questions.
Before I'm the chair, I'm going to give you a little gift. It's, of course, dust. No.
Norwegian dust.
It's French dust. French dust, sorry.
French dust.
Yes.
It's Pascal dust.
Yes. Don't share.
Wow. It's the best kind of dust. The chocolate kind.
I will now allow questions. Before that, I have one important message that as last year, I forgot. And that is that for the people who are going to the dinner, the buses are going from Multikusmusvei. Oh. Speaking Norwegian and English at the same time is a little difficult. Number 35, which is just behind here. There'll be 2 buses at 5 o'clock. So those of you going to dinner, please show up there. All right, now.
If you missed the dust, you missed,
If you
missed the bus. If you missed the dust and the bus and the dinner.
That's right. So, do we have any questions?
So if dust indeed comes from high mass stars, presumably they'll be very hot and have lots of UV radiation. Wouldn't that destroy the dust?
I mean, that's a very good question, because, I mean, if you would ask me, will high-mass stars be able to produce dust? I would say no, because high-mass stars have a lot of UV photons, they have lots of all kind of, and they have no elements, because, I mean, the elements are formed in the center, right? So what elements are present in the outer layers of these stars? So I don't get this picture, and I don't get that there's 156 of these stars looking like this. And I mean, with the risk that I've done my analysis completely wrong because it hasn't been published yet. So assuming that I did it right, then what I get within the uncertainties that we don't know the distance to very many of these stars is that they are capable of producing somewhere between 0.01 solar mass to 1 solar mass of dust. So that means they can either, at best they only account for 10% of the dust in the Milky Way, and at best they can account for all the dust, and at worst they have to be counted in as about 10%. But I have no clue what kind of dust this would be, because presumably it's carbon or silicates, because that's what we see most, but these type of stars might have other types of dust. And if you look at Eta Carina, which is a similar type of star in a similar kind of phase, also doing dust puffs, we just can't work out what the dust should be, because when we look at spectroscopy, what we get is nitrogen, and you can't really make very exciting nitride dust to our knowledge. So we are actually completely bewildered. What type of dust is this? I mean, so this is an observation going, the dust seems to be there, but we don't know what it is, and we don't know how the stars do it, or why it's not destroyed, or anything. It's really weird, in the good way.
Anybody else? Oh.
Well, could this have something to do with this pulsating pair instability supernova? This ejection of the external shells before the supernova occurs?
So we know very little about these stars. So we actually don't know what mass they are. We don't know how old they are. We don't know what distance they are, right? So maybe even though we see 156 sources which look similar, I mean, I have nightmares thinking some of them could be planetary nebula, some of them could be LBV stars, and some of them could be Wolf-Rayet stars. So I think I see the same phenomena, but I'm actually looking at 156, but 5 different types of stars, and I'm trying to, so that's why it's not published yet, because somehow I'm thinking I need to address that, because else the referee is going to kill me, right? So there's a lot of there's more open questions than I would say clear answers on these stars yet. And what I don't understand is that none of these 2 authors have actually published anything on them since. So either I'm missing something completely obvious that they know, or else they just found them boring and thought, who cares about the dust, because they actually work on something else. So if you never see a paper from me, you know why. It's because there was some completely uninteresting answer that just wasn't worth writing about.
See any other hands? There we go.
So we heard a lot about dust and gas. So what is the difference from which size or cluster molecule size do you call it dust? And what is
that's a lovely question. So the question was, when is something a gas? When is the molecule? And when is it a dust grain? And that's actually a very good question, because there is sort of a transition from being sort of a small molecule to a big molecule to a macromolecule, and then suddenly be in the solid phase where you are at solid material because you have a solid structure. And that's probably different from the different materials. And I have approached several solid-state physicists, both at Uppsala University and at Copenhagen University, saying, I would like to know for silicates or soot or whatever, what is the transition? And they go, oh, that's easy, we can calculate that. And then they start, and then I come back and say, have you calculated this? And then there's like all kind of problems, so I don't know the answer. So the best answer I have is, it's somewhere between 300 and 500 atoms, that once you get to about that size, then you start seeing a solid structure, and then we call it a solid. So it's mainly has to do with the bonding, because that's important for how it interacts with the light and how it absorbs the light. Because you have fewer degrees of freedom in.
So, if there are no more questions, then I think we should thank our speaker one more time.
And then I would like to thank for the cake, because the cake is just the prettiest cake I've ever seen.
Of course, I forgot one important thing. There is a sale of books.
Ah, that's right. Yes. So.
Where?
I don't know.
There we go. Right
Okay.
there. So please go buy some books. That'll make both you and the person you're buying it for happy.
But they're in Danish. I have to warn you. So there's some children books. So if you have some kids and you want to teach them Danish, if you have no hard feelings about Danish, then and then there's also a book for adults about sort of basic astronomy and the meaning of life and everything.
But as we all know, as long as it's not spoken, Danish is a language that is possible to understand.
But you guys spell it so much better than we do.